Pratt KMP algorithm for string matching, which has a complexity of m plus n. So, how does the algorithm work? We have this text pattern. First, for the pattern, just using only the pattern, we do not need the text for this. We compute for every location of the pattern length of the longest prefix of the pattern, that is a proper suffix of P1 to Pi, right. So, the motivation for this is that if I manage to match up to this point with the text, and if there is a mismatch here, then how much do I shift my pattern for the next alignment. This number, which tells you that the longest proper suffix, which is a prefix of the pattern, tells you that that much you have already matched. So, that is the length by which you will shift the pattern, and then you will start comparing with the next character of the text with whatever after the shift, whatever the next character of the pattern, you are going to compare it. So, we did this example, we computed pi. For example, if you look at position 4, if this is my prefix of the pattern, then the longest proper suffix, the length of the longest proper suffix, which also happens to be a prefix of this P1 to Pi, is 2, because AB is the longest proper suffix of this prefix, which is also a prefix of the pattern. Okay, so, when I move here, the longest proper suffix is ABA, which happens to be the prefix. So, that means that if I matched my text up to this point, and if there is a mismatch here, how much do I have to shift? I know that, for example, that this is A and this is B and this is A. So, I just start with my 4th character and start matching with this. So, that is what gives me this number 3. So, the KMP algorithm goes like this. First, given the pattern, compute pi. Okay. How do I compute pi? That is another subroutine, we will get to that. After I compute this pi, then I am running through, I am going to run my text, and so start with my text, and if my next character, if my first character of the pattern and the text match, I move both Q and then I come out of the loop and I also gets moved and I start matching the next character. So, I keep checking my pattern with the text. So, whenever there is a match, Q improves and I come out of, I go to the for loop and I also improves. I am just checking one by one. But when there is a mismatch, then while Q plus 1 is not equal to Ti, the next character of the text does not match with the next character of the pattern. It is this kind of a situation. Then I use pi to do some shifting, right. So, Q now is, and Q is greater than 0, Q is pi of Q. Pi is defined only for values greater than 0 anyway. So, I keep shifting and eventually I may even get to 0, that there is nothing matches here. So, I start from fresh next character and with P1, Q might become 0, then I am just checking P1 and Ti. If it matches, great. Even if that does not match, then I move on comparing P1 with the next character of text. I changes, Q does not change if there is a mismatch here, so which is all fine. So, that is what you expect, and that is essentially the first naive algorithm we started off with the extra information about the pattern, which tells you that once there is a mismatch, I do not have to just shift one character. I can use my pi function to shift my next alignment by a huge number, and so because it is essentially the naive algorithm, the correctness proof goes through. But as I said, there are like formal, one can give a proof of that pi function is correct, and using the pi function KMP is correct, and inductively. So, we won't get into that. So, I did all that. modulo the computation of pi, I was trying to argue last time that this, even though there are n steps in the for loop, this is a constant time computation, this is a constant time computation. It is possible that this while loop is non-constant, it goes through several steps, but despite that the overall running time is only order n, and we were trying to argue this. So, one way to argue is using an amortized argument or a potential argument. So, claim amortized cost in each iteration of the for loop is at most 2, actually, I mean more like it is constant. And if I show that, then I know that at the end of this n loops, the overall running time is order n. The reason we need to argue is that there is this while loop which complicates things for us, because it is possible that in one iteration of the for loop you are doing a lot of the steps here. So, naively this could be as bad as m, which sounds like an NM algorithm, but there are some properties of this pi function which helps us to actually argue that this running time is not mn, but it is more order n. Okay. So, how do I argue this? Using a potential argument, let the potential of my data structure is the value of q. The data structure is nothing, basically q is a variable which keeps changing, and I say, let us say q is the potential, then we know by our mechanical formula that the amortized cost is actual cost plus the potential difference, right. So, in this case the actual cost, I am just comparing and incrementing it. So, that is 1 unit of time. Now, the potential value q increases by 1. So, actual cost plus the potential change is 1 plus 1. So, this is 2. In this case the actual cost is 1, some comparison, something happening, and q decreases. So, the amortized cost is 0, right. Amortized cost, recall, is actual cost whatever the potential afterwards compared to. So, so now the interesting step is here. So, suppose the while loop takes some k steps, right. Then at every point q decreases, after one execution of the while loop q comes down at least by 1. So, if you do k steps, q comes down by at least k. So, q decreases so amortized cost, which is equal to actual cost plus the potential difference, is less than or equal to k minus k, which is equal to 0. So, because actual cost is k, but the potential decreases by at least k. So, it is also less than or equal to 0. Okay. So, what is the intuition here, right? So, where do you see this while loop? Suppose I got a mismatch here. I matched up to this point, or maybe not even whole thing, but I matched up to this point, and I have a mismatch at this location. So, now what this algorithm is saying is, okay, shift by a quantity and compare the next character with this I. Maybe there is still a mismatch, shift by another quantity and keep. So, in the worst case, maybe the shift is happening only one step at a time. So, I may be making something like m comparisons with this one location. Okay. Naively, then you might just simply say m times n is the running time, but the argument is that at every time your q changes. So, next time when you hit something like another m comparison, it will be at least far away, it will be at least m steps away, because every time the amount of match you have got is fewer and fewer, right. So, because when pi shifts things, then I have only 5 characters, and then another shift will tell me that I have matched only 2 characters, 1 character, things like that, right. So, now it is not possible that in maybe if there is a mismatch here, I will be doing some m comparisons, because I have only matched only very few things. So, I will be doing only that many comparisons, unless I have gone very far away, I have done so much match. So, that means that if you hit with one cell some m comparisons, it that can happen for at most n over m such cells. So, that would give you an order n time. Okay. You can see it in multiple ways, because if you execute while loop several times, that means q becomes very close to 0, it is getting decrease. So, you cannot have another while loop taking so many steps, because q value has to be greater than 0, that is it, right. It is the same analogy, same idea here. Okay, good. So, the algorithm is fairly simple with the understanding of pi. The analysis is a little subtle, but overall it gives you an order n time. Now, everything now boils down to computing pi. How much time does it take for this step? Given a pattern, I want to compute pi, which is this, right. It turns out the code is very similar to the actual computation of the string matching itself, except now you are matching your pattern with the pattern to compute pi. Here we are computing pattern with the text, here you are computing pattern with the pattern, and so this is the code. You will see pretty much an analogy with this, right. Pi of 1 is clearly 0, we can make that assumption that the longest, I have deleted it, proper suffix. So, there is nothing, proper suffix is only an empty string of a 1 character symbol. So, pi of 1 is 0. Now, so let us see, I am here, pi of I, right, location, I have P1, P2 up to Pi, and I want to compute the longest prefix of the pattern, which is a proper suffix of this, right. Okay. I want to compute P of I. And I have computed, let us say P of I minus 1 is some pi of I minus 1 is what is k, right, because when you get out of this, you have actually computed pi of the previous character, and that turns out to be k, let us say. That means that there are these k symbols here, which happen to be a prefix of the pattern. So, now if this character matches with p k plus 1, then you know that my pi of I is k plus 1, right. So, that is what you are trying to compare. Compare p k plus 1, because I know that p 1 to p k matches with the last I minus 1 characters of here. No, the last k characters of p 1 to p I minus 1, right. So, let me just write down what I am saying. Pi I minus 1 is equal to k implies p 1 to p k match with last k characters of p 1 to p I minus 1. So, now if I just look at p I, that is what is happening, and p, so this is p 1 to p k. this is P1 to Pk, and this is I minus 1, and I am at ith location. So P1 to Pk match with the last k characters of this. So if Pk plus 1 matches with the ith character, then I know that I have one more, pi of I would be k, the one, k plus 1. So I add k to k plus 1 and just simply say pi of I to k. But if it does not match, I know I have, so I am trying to match with the prefix of the pattern, and I know that I have matched so many characters here, but this guy does not match. Then exactly like the way we did the pattern matching, I would apply pi of I minus 1, which tells me how much shift I have to do, right? That is what we are doing. So pi of I minus 1 was k anyway, so I would just do pi of k, and that tells me a new k, that tells me how much shift I have to do, and then compare with the next character. It is very similar to what we were doing with the pattern and the text, here comparing pattern with the pattern. And so it is essentially the same code. We are just comparing my next character with the prefix of the pattern, and the moment I found a match and incremented it, my pi I is going to be k. Okay. It is possible that I get out of this while loop because k is 0, and again if I find the next guy match, at least I will get a 1, otherwise it will remain 0. Okay. So that is a computing pi, and the same argument tells you that this is an order m. Right. This is order n. Right. The same kind of a potential, k would be my potential, k is greater than or equal to 0 all the time, and k is increased only here. So when it increases, imagine that you come up with a charge of 1 to pay for the decrease, and when while loop is executed multiple times, k keeps decreasing to compensate. So the amortized cost is constant, so it is an order m time. Okay. So it is a very simple modification of the naive algorithm by saying, okay, do not just shift by one character, you know how much you have matched, and based on the pattern you should be able to know how much you have to shift, and the analysis that it actually gives you in order m plus n is a little subtle, but it just works. Okay. So, and this is pretty much what you can aim for. You have to look at the pattern, you have to look at the text, and so it is sort of an optimal algorithm to not just find one occurrence, all occurrences of the pattern. Okay. So now so there are a lot of variations of this. What if you have mismatch? What if you have some, if I do not want exact matches, but if I allow some k mismatches, if I allow some wildcard characters and so on, there are hundreds of papers written on this, and it is still an active area. But I am going to just shift focus to slightly different kind of notion of the same thing, which is the notion of indexing. Right? So what would you be interested in a data structure perspective, right? So if you look at the automata based algorithm we saw, where you given the, or even this KMP algorithm, given a pattern, I compute something in time proportional to the pattern length in order m, and then remember, once I compute this takes order m time. Now suppose I change the text, right? This code which I wrote down here works for any text, right, in order n time. So this is one pre-processing I compute given a pattern. Now you give me any other text, this in order n time I can find all occurrences of the pattern, the same pattern is fixed, right? So in imagine you're checking in an editor, you have a word you want to search in multiple different files. So it's like you're spending some time proportional to the pattern length, and then after that your search time is proportional to the text length. It doesn't depend on the pattern. Okay. But this is not an interesting kind of a data structure question that happens in practice. It will be the other way, that I give you the text in advance, right. So, let me just write what. So, automata based or this pi based, which is pre-process pattern in order m time, so that given any text, so that means text changes, text is my query. Given any text, we can find all occurrences of P in T right. This is a spin-off of the KMP algorithm. It simply says that, once you have spent your time and pre-processed it, now I can run my text now. But in practice, you would actually have the other way, that I give you a text in advance, right. There is this huge file I am editing, or maybe dictionary, or imagine Google applications where it has text is a collection of all website addresses or strings and so on. So, you are given pre-process the text. I do not know how much time you want to spend, so that given any query pattern, I want to find all occurrences of pattern in order length of P time, right. I mean, imagine that this is your collection of all websites and strings in the websites and so on. Now, you give a query and you want to find out all websites that contain this query in time proportional to length of your query. That is what we want, right. In particular, I do not want to spend time proportional to the length of the text. Okay, that is huge. So, this is not automata or pi base. This is what in practice we need the following problem solved, right. Pre-process, I give you a text in advance, pre-process and whatever time, we really do not care so much about the pre-processing time, because that is a one-time thing. And then when the query comes, I want to be able to answer this query in time proportional to the length of the query, right. So far, whatever we have seen really does not address this question. Okay. But there is a very elegant way to solve this, and that takes us to this notion of suffix trees, right. Okay. So, before I talk about suffix trees, let us talk about tries. Right? Try is a data structure for a collection of strings. Okay. So, it is a version of tree, and tree for strings. So, let us say, okay, let me just give an example and then. So, I have this set of strings which I want to store in some tree. Okay. I mean, why do I want to store, and how do I want to store, depends on the query I want to ask. I will get to the query later. I mean, typically the kind of queries is given some small string. I want to know whether it matches exactly one of the strings. It's like a dictionary problem, right? Given a string, is it there in the set? Or is it a prefix of some of the strings in the set? These are the kind of questions one I'm interested in. So what is a trie? It's a rooted tree with labels on the edges no two children of a node has the same label. Every leaf corresponds to a string. In the set S. And if you concatenate the labels in a root to leaf path, it is a string in the set. And there are, number of leaves is so for example, a trie. So it's all, given all these conditions, there is a unique trie, and a trie for this set would look like this: that I have a root A, B, C, D, and this corresponds to string number 1. So let's say 1, 2, 3, 4, 5. I'm just giving some numbers to these sets. Okay. Yeah, okay. So from C you drop a D and you get 3. Sure. Right? So A, B, C, D corresponds to the third string. A, B, B. So I mean I could do this. It will violate some condition, right? It will violate this condition that no two children of a node is the same label. So if you have somebody of the same label, you might not want to use it. So A. So the way to construct it is, the way I'm actually doing it. So insert one string at a time. So this corresponds to string number 2, and BBAC. So there is nothing B starting from here. So I'm going to do BB. That corresponds to 4, and BACD. So this is a trie for the set of 5 strings. It has 5 leaves. Each leaf corresponds to a string. You read from the root to leaf node, that path, concatenate all the labels that corresponds to the corresponding string. Yeah. So what can you do with such a trie, right? What kind of queries can we ask? So queries. So given P, is it in S? So I give this pattern query B, and I want to know, let's say, A, B, A, C. Is it in the string, in the set at all? Is it in my dictionary? So, how do I answer this question? So, I start from here, so basically the children of the node, each one has a label. So, I look at my child, and so there are many ways to represent this. So, you can think of it as a sigma array tree. So, imagine that if your character sigma is 3, then there may be an AB and there is an empty C, right. This is an empty tree. So, then you should be able to just go to my child labeled A if it is there at all. So, I go to child label A, and that has a bunch of children. So, I go to child label B, and then that has a bunch of children, that there is no child label A. So, I know A, B, A, C is not there. And how much time do I spend? Proportional to length of this pattern, right. Yep. Okay, good. It depends on how you are representing this tree, right. I am just sort of, so if you think of it as a k array tree or a sigma array tree, then I can directly go and index into my child labeled certain thing in constant time. So that's, there are many ways to do it. Like I said, one is that I assume that there are sigma slots at each node. Some slots are empty. So, think of it as an array with some nil pointers there. So, I know first one corresponds to first character, second character, third character. So, I can directly get an index into the array and just go to that ith character and whatever I am looking for. But that will take a little bit more space actually. There is another way, we just say, okay, I keep only the non-empty children characters there, maybe in some order. So, I can do a binary search there. So, it will not be sigma times, but it will be a log sigma here, right. So, I come here and I have to figure out B. I do not know where B is. I have stored them all in some order of the non-empty children I have. I will do a binary search to see is there a B, and then if so, I will proceed. If not, I just say it is not there. Okay. So, you could, depending on this is the time space trade-off. If you have represented empty slots, it takes more space, but you save on this time, but otherwise it takes less space and you save on the time. What other query can I answer? Okay. Suppose I want to answer, this is one, given P, is it a prefix of some string in S? Okay. I mean, this will tell you whether it matches there if I get to all the way to the leaf. If you are asking for a prefix of some string in S, same thing, right. You just follow from there. So, for example, I am asking for ABC. Is it a prefix of some string in this? Then I follow through A and follow through B and follow through C, and my pattern ends here, and but I am at a nice node. So, the answer is yes, it is a prefix. Boolean query is easily answered, but if I actually want you to give me the output of all the locations where which are all the strings for which I am a prefix of, what should I do? So, you can answer this in order P time, but if I also want to know what all the strings for which I am the prefix of. Yeah, number of children will tell number of leaves. Number of leaves will still tell me the number of strings for which I am a prefix of. But if I actually want the strings, I just go down and check and find all the leaves, and okay. So, that's going to take time proportional to P plus this subtree size. Okay, that's a little dicey thing. We'll get to how to improve this. Okay. But so let me add that remark. So, this is again use the word locus. So, I am saying if you only care about how many strings for which I am a prefix or if you ask me is there a prefix on which I am, is there a string on which I am a prefix of, I can just follow through the thing, get to that node and I will output in order p time. How do I answer the counting query in order p time? Sorry? Storing the number of leaves, right, in your pre-processing, right, not children, number of leaves, right. So, you know it is all part of the pre-processing. I mean, after you build your trie of all the suffixes, at every internal node you just go and compute and store, if you do not care about space, store the number of leaves in that subtree and store it there. So, now in the query time you can count the number or you can count the actual Boolean query in constant time in order p time. Right. Remember this, the counting is also very useful because remember when you query something in Google, it does not necessarily give you everything, it just gives you some sort of a ranking, right. Okay. Ranking and as another possible query, right. You just define some sort of a ranking of these pages and I want to give the top k ranked ones, right. So, there is so much work here. So, sometimes it is useful to know the number before I ask for the actual list of output. So, if I really want all the locations, so how do counting, let me note that store the number of leaves at every internal node in pre-processing. Now, so what is the locus of the point? It is that node whose root to leaf path if you concatenate the labels, so root to that node path is P. Right. So, this is locus of ABC because you just if you concatenate the labels on the edges of the root to that node path, it is ABC. So, one thing I did not talk about is how much time does it take to build this trie, okay. And how many nodes are there, how much space there, right. How much time? Well, you can actually insert one string at a time exactly the way we did, right. We just follow through my existing trie and search for the longest common prefix of my string with this by following through this, and then the place where it branches off you just go and create new nodes and put it in. So, it will take order whatever the length of the string. So, overall construction time would be order of summation length of the strings in the set. And this could also be, in the worst case, a number of nodes in the tree. Every time you might be just generating new nodes. So, is this clear? So, I have a set of strings, each string has a certain length. I am just saying, just go insert it into this trie in taking time proportional to the length of the string. So, in the worst case, the overall time for your construction will be sum of the length of the string, and that could also be the number of nodes in the tree, because every string may not even share any node, it is all creating new vertices in the trie. Okay. Now, there is the notion of compressed trie. Okay. And that is, why do I need nodes with one child? I just compress them and put the concatenated label on the edges. Okay. So, that means every node has at least 2 children. I ensure that every node has at least 2 children, every node other than the leaf has at least 2 children. Otherwise, I concatenate all of this, for example, would become one child with like this, with the label now BAC. Okay, so, this would become whatever that number was, 5, and so on. Okay. So, here for example, this would become BC, and then it will branch to B and D. So, ABCB, ABCD. Right. The query algorithm, everything will be the same. Now, you are going to be compare with not just one character, you will look at the entire string there, and if there is a mismatch in between, you just get out and say it is unsuccessful, it is not there. All right. That is not the problem. Time again, at the time of insertion itself, we can do it. That when I hit there and I find that at the time of insertion, I just put the entire string there. So, insertion is actually easy. Now, let us say I want to insert ABD, right. I want to insert a string ABD. I will start here A and B. Now, I have to branch. So, here now I will create a new node with C here and D here, and then follow through. So, it will it will be the same as. So, it will now. So, I am just sort of breaking the edges, creating new nodes, because now there is 2 children are coming in. But what effect does it have on the number of nodes? So, construction time is more or less the same. In fact, it might be little better, because once you create your own follow through and create a new node, you just put the rest of the symbols and create one edge out there. But how many nodes are there in the tree now? That is what I want to understand. Compressed trie is replace path of single child by an edge with concatenated labels. Now, the more important interesting question is the number of nodes in the compressed trie. In the process, clearly it was sort of like, sum of all length of the strings, but was the initial number of nodes. But now I claim it has become much smaller. How many leaves are there? Yeah, if the string has n, if the set has n strings, number of leaves is n. What can you say about a tree with n leaves, where every node has degree at least 3, every node except the leaves? Okay. So, let me just write some lemma, which is a nice combinatorial useful lemma. Let T be a tree with n leaves such that all internal nodes have at least 2 children. Which means that essentially there is no degree 2 vertex in the tree except for the possibly with the root. Okay. So, can you have lots of nodes? What's the average degree of a tree? What is the average degree of a tree? So, average degree is, which is roughly 2 into n minus 1 by n, which is at most 2. Right? So, a tree on n vertices is at most n minus 1 edges. Okay. So, average degree of a tree is at most 2. Okay. So, if you have a lot of, if you have a degree 3 vertex, so here is the argument, but you should actually formally prove. If you have a degree 3 vertex, you should have a degree 1 vertex to compensate, right, because the average is 2. If you have a degree 3 or more vertex, there must be a degree 1 vertex to compensate the average degree, because the average degree is 2. So, you cannot have too many degree 3 or more vertices. It is bounded by the number of leaves. So, number of nodes is at most 2n. More importantly, like here it's, yeah, actually I would say 2n. This is, any tree, graph theory tree, just it's a very nice combinatorial lemma. I mean, you can argue by, I already argued it, right? You just do sum of the degrees is this, and let's assume how many vertices of degree 1, I already told you. How many vertices of degree 2, maybe 1, how many vertices of degree 3, the rest of them, 3 or more. Do some degree argument and you will see that you cannot have too many nodes, because every internal node has degree very high, but there are only n minus 1 leaves. So, if I have too many of them, then the average degree will come down, will go up. Okay. So, proof. Okay, it's a nice discrete math exercise. Yeah. It's not everything is 3, it could be more than 3. The rest of them can be more than 3, but that works in your favor actually. Yeah, that works. Yeah, so the inequality works in your favor. That's it. So, you just argue, and so the bottom line is that this compressed trie, by just making these entire paths of single child into an edge, I now made the number of nodes in the tree to be order number of leaves. Okay. So, now let us just come back to this running time. If I want to know whether a string is a prefix of some string in my given set, we already argued that the time it takes is order p plus the subtree size of the locus of p, right. So, it is like this, right. So, I want to know whether AB, so I have done AB, then I will do a BFS or DFS or in this subtree and output all the leaves. That is my output. Output is exactly the leaves in this subtree, because those are the places or the text strings, input strings for which I am a substring, right. Actually, I am a prefix, right, not substring, I am a prefix. So, the time spent is proportional to whatever pattern size plus the subtree size. Now, what can you say about the subtree size? How many nodes can there be in the subtree size? Use the same argument there. It is. If there are k leaves here, then it will be proportion. It will be like 2k. So, this is nothing but plus number of occurrences of p, because this is the number of leaves in the subtree, right. So, after I have done this, if in the compressed trie, now time to check whether a string is, what are all the strings for which I am a prefix. You run through and then do a BFS or whatever and collect all the leaves in that subtree. The total time is proportional to the number of leaves in the subtree, because the total number of nodes is proportional to the number of leaves in that subtree because of this compression, and number of leaves in the subtree is exactly the number of occurrences of the, it is the output size, right. So, nobody would complain about spending this much time, because this is the output size. I have to output each of this leaf. So, you are just spending time proportional to the length of the pattern plus the number of occurrences. Okay, good. So, I still have not told you about suffix tree, right. So far we are working on a collection of strings. Somebody has given me a collection of strings, and from that collection of strings I construct this trie, compressed trie. Here I can answer these queries, that is my string in the trie in order p time, or if it is a prefix of some string, all the locations for which it is a all the strings for which I am a prefix, I can answer them in order p plus the number of occurrences. Okay, and okay, how much time does it take? Suffix construction time is still, in the worst case it can be, well, it is not clear, we will see. But the good thing is the number of nodes in the tree is proportional to the number of leaves in the tree. Okay, so now let me just talk about suffix trees. Right? Okay, now I am interested in my pattern matching query. Right? One text is given, I want to pre-process it, and query patterns are coming, and I want to know whether a pattern is in the text or not. Right? So, here is a pretty complex observation. P is a substring of T. This is what I am interested in. If and only if P is a prefix of a suffix of T. Right? Complex observation. Trivial observation, right? P is a substring of T means what? That so here is my T, P is appearing from here to there, which means that P is a prefix of the suffix starting at I, right? So, now the idea is like build a trie. So, suffix tree is simply a trie of all suffixes of suffix tree of T So, take your text, look at all the suffixes, right. How many suffixes are there? If the text is of length n, there are n suffixes. The whole text starting from position 1 to n, 2 to n, 3 to n, 4 to n, and then n alone. These are all the suffixes. Think of this as my collection of strings, right. Build a trie like this for not just for the text, but for all the suffixes of the text. Now Now, I know I can answer this question given a pattern, is it the prefix of some string in S is the same as asking is P appearing in S in T, right, because P appears in T if and only if it is a prefix of some suffix of T, right. So, I can answer this time in order P plus the number of occurrences P by building a trie of all suffixes of T. I will just go on, and the leaves would correspond to all the suffixes for which I am a prefix, which means that it tells you all the locations where this pattern is appearing. Okay. So, let us quickly do an example. So, if my text is some and the pattern is not given, pattern will keep coming, right. So, given the text, I take all the suffixes. So, what are all the suffixes? So, let us number them. So, one suffix it will be A, which starts at position 10. Another suffix would be BA, which starts at position 9. So, that tells you this. Another suffix would be CBA. So, if I want to do the compressed thing, then I would just put them in like this. See, BA will be 9 and compressed would be CBA starting at 8 and then BCBA. So, I will break it here now. A would be 9, BCBA would be 7. So, BA corresponds to 9, BCBA corresponds to 7, ABCBA, aha, I have a problem now, right. What is the problem? Let us see. So, ABCBA would be, I just create something here and say BCBA, and so that is ABCBA starting at position number 6, with something ugly going on, right. I want every leaf to correspond to a suffix, but yeah, who will correspond to A in particular. So, what is happening is you have one suffix which is a prefix of another suffix, right. A is a suffix which is a prefix of another suffix A, B, C, B, A, and so I lose the chance to be a leaf. Okay. So, way to handle that, anybody has seen this? Yes, we create a dummy character. Okay. So, CBA dollar, this will be A dollar, then I will have an A dollar here, which would be 10, not this guy, right. This would correspond to a leaf, because now no suffix would be a prefix of another suffix, because this is a new character which does not appear in my alphabet at all. So, we create a new dummy character. So, now this corresponds to okay, and then ABCBA is what I finished with, AABCBA. So, I would create that is suffix 5, then starting at B. So, I would have ABCBA dollar would be 4. And ABA would be so no, this is 2 and so on. Okay, so this first one would be AB, so second one would be no, this is 3. So A, B, and then A, B, C, B, A dollar, and then 2 would be starting at B, A, and then B, A dollar, and that will be 2, and then 1 would be somewhere starting at A, B. So I will break here with an E. And this would be A, B something. Okay, so that is the suffix tree for the text, which is containing all the suffixes of the text with the dollar added. So you can also add dollar as method. So it's a compressed trie because no internal node has one child. Every leaf corresponds to a suffix. No node has 2 children with the same label, and so on and so forth. Right. So now it has order n nodes. And pattern query takes order m plus number of occurrences. Right. I follow through the P and get to an internal node if I am successful, and then I go and do a BFS or something on that subtree and pull out all the leaves positions, and that gives me all the occurrences of the pattern. Okay. Now construction time. Naively, the way I have been doing it, it could be as bad as order n square, but there is a quite a non-trivial construction algorithm which can be done in, there are several. It's because you're not inserting arbitrary strings. You use the fact that it is a suffix of a particular text. So you can take advantage of it, right? I've inserted something, I know the next suffix is coming, so it will match with this suffix to a large extent. So I can do some careful pointers and eventually construct the whole thing in order n time. Okay. So here is, so this is something we are not going to do, but there are lots of books. So for example, there is a book by Dan Gusfeld, algorithms on trees, strings, and sequences, or some such thing, which has 6, 7 chapters on suffix trees and applications. Okay. So, a couple of other remarks. If you look at the leaves, if I have done this correctly, no, I did not do this correctly. Okay, so let's. If you read the leaves from the left to right, so let's say I have in the children of each node is ordered according to the order of the characters. Okay, so you have an ordered alphabet. Okay, A is less than B is less than C is less than. Let's assume your dollar is smaller than everybody else. You can also, as you use the convention, dollar is bigger than everybody else. I think the way I have drawn, dollar is smaller than everybody else. Then, if you write down all the suffixes, what are the suffixes? So it's dollar, A dollar, B A dollar, C B A, and so on, and lexicographically sort all the strings. Okay, so write down all the suffixes. Each suffix is a string. So, use a dictionary order to order the strings, right. So, for example, A delta will be smaller than B A delta, B A delta will be smaller than C B A delta, because the first character this is bigger. B C B A delta will be smaller than C B A delta, but bigger than B A delta, because it is bigger than B, the second character is bigger. So, you use the lexicographically sorted order of the suffixes. Then, if you read off these levels, this levels 11, 10, 5, 3, 1, 7, 9, 4, 2, 6. Is it 7? I don't know what it is. I have also 7 here. This is probably 6. So, if you read these suffixes in this order, that actually gives you a lexicographically sorted order of the suffixes. Okay. I mean, it's no magic, because I have, if I order each child of every node in an ordered fashion, order them in that smaller to bigger fashion, then the first leaf would correspond to the smallest suffix, smallest in the lexicographic order, and then the next, second, third, fourth kind of things. So, this permutation, so what you have is a permutation, and that also has a name, it is called a suffix array. It is a permutation of 1 to n. With pi of I equal to j means that the suffix starting at j is the ith smallest suffix. So, this is the smallest suffix, and then second smallest, third smallest, fourth smallest, smallest in this lexicographic order. And people have, so one of the problems with suffix trees is the space it occupies. Even though I said it is order n nodes, if your character length is n, this could, if you do some calculations, it could be some 10 times n, because it is not just about number of nodes, each node has some edges coming out of them, and each edge has a label associated with them. And if you actually in practice go and verify, 5 times, 6 times the length of the text is what the suffix tree takes. Okay. Now, in the last 10-15 years, there have been a lot of progress on reducing the space of suffix trees, very good progress, they have all been implemented. But in the early days, when suffix trees are implemented, people were happy to use just the suffix array to do your string searches without the tree. So, I don't, which means that I just keep only the leaves in that order. Now, I can do binary searches on the suffixes, right. If I just think of them as I have all the suffixes ordered, right, then I want to know whether my text is there, I just go and check compare it with the middle suffix, and until I get a mismatch. If I get a mismatch, I just go to the left or I go to the right, right. So, this won't be taking time proportional to length of the pattern, because there will be a log factor coming in, it will be more like m log n. But space wise, I just have to remember only the permutation, okay, just the suffix array. Now, there are a lot of work on compressed suffix trees, compressed suffix arrays and so on, putting all of this together. Okay, so one other remark, that it is not just for string matching. Suffix trees are useful for number of applications. So, let me just give one. Okay, so suppose I want to find, so I give you some string and so on and so forth, and I just want to find some common substring and the longest common substring among all of these strings. Okay. Oh, I mean, just think about it. It's not that easy at all, right? Even for a pair of strings, okay, maybe for a pair of strings you can do it, but I want it to be common to all of the strings, and I want to find the longest common strings. Okay. Without suffix trees, it's not even clear how you would go about doing this. Okay, how do I use suffix tree to do this, right? So, what I can do is I construct what is called a generalized suffix tree, right? So, put all the suffixes of every string and create a big trie. Okay. So, construct I mean, this is possible in time proportional to the sum of the strings length, because all suffixes of S1 I can construct a suffix tree for S1 in order S1 time, length of S1, and similarly for S2 and build all of it, right. So, you will have this huge suffix tree. Now, at the leaves, what do I have? Okay, I mean, you also need some delimiting characters between these things, right. So, imagine you have this big string, which is a concatenation of all the strings with some delimiting characters, which does not appear inside in any of the string, and I build a suffix tree. Leaves correspond to positions in the string, right, in this big concatenated string. You can break it up into ith position of jth string or something like that, because if you have this one big string, so let us say the first string has 10 characters, second string has 17 characters, then I know that if this position is like 21, I know it is like 11th position of the second string, because the first position is first string has 10 characters. So, I know from this position which position and which string, right, I have them all. So, I have constructed this huge suffix tree, spending this whole time. Now, what is the question? How do I answer this question? I want to know what is the longest common substring, or let us say, how do I find a common substring? What is a common substring? And then we will get to longest. No, so I have this, so take S1 $1, S2 $2, Sn $n is my huge text, okay, and I construct this big suffix tree for them. Okay. So, do not worry about ij, each leaf has a certain position. Okay. Now, in this big concatenated text, it gives me a position, right. So, based on the length of these strings, I know given the position, which string it is, that is not a problem, right. This has length 10 and this is length 17, this is length 15, then I know if I am asking for a 25th position, that is what a leaf would tell me. 25th position is essentially 14th position of S2, right. So, it is that is the I and J, I am just saying 14th position of 14 comma 2. So, all I am saying is from the leaf you can figure out which string it is in. Okay. So, now what is a common string? How do I find a common string? Remember, this is not a data structure problem, it is not about pre-processing, it is just about one time I want to solve this. Given this string, I construct this huge tree, and how do I find any common string? Looking at the suffix tree, what does it mean by a common string? Okay. So, let us say this string is a common string, what does that mean? Yes, how do I figure it out from the suffix tree? In the leaves, what am I looking for? So, in the leaf of this subtree, so again that is why I am breaking it up into I comma j is useful, right. So, jth position in ith string, suppose that is what I break each position as, okay. Then I am looking for a node in this whole tree, right. I am allowed to spend time proportionate to the whole thing, does not matter, it is all pre-processed. I am looking for a node whose subtree has leaves with I for every I, right. It should appear in the first string, second string, third string, fourth string, every string it should appear, right. So, I am looking for a node whose leaves of the subtree contains I for every I. Okay. Now, this is something I can actually do. So, after I construct this thing, I do a post order of this whole tree starting from the leaves, okay, and store the set in every node, store the set of all strings where I appear, right. So, construct, do a post order and compute and store at every node set of strings in which that node appears, right. The node corresponds to a substring and that can be done in post order, right. So, I open up a set here and all the sets I see I just collect it and put it here, right. And then as I just go up, it is just the union of the sets here, right. Take the union of the sets and that comes here, take the union of the sets that comes here, that is it, right. So, now I will just do a pre-order of the whole tree, looking at the sets and see is there some node where every string is appearing in that set. Then I remember the depth of that thing, because the depth corresponds to the length. I am looking for the longest common string, right. And in this whole process, I will find one node which has the entire set and which has the longest prefix. Okay. So, I mean it is a simple exercise in some sense. If you can think in terms of generalized suffix tree and understand what is happening in suffix trees, but if you just omit suffix tree and think, so now overall running time would be essentially proportional to order sum of the lengths of the string, and which is which is reasonable. But if you do not have this, I can't imagine how you would find common substring between even pair of strings. Now, I want some string which is common to everybody and longest. So, suffix trees are very powerful in terms of what they store and not just useful for doing pattern match. There are a lot of places where it is useful. Okay, so that is the story. Okay. So Gus Field's book, for example, will have many applications of sophistries, and that's actually really used in computational biology among other areas, text searching, various other places.